We're on lesson 2 of chapter 3, which will have us graph linear equations. First we'll check solutions to equations, then we'll graph equations and values, and then we'll do a linear function as well. Before we move on, a couple of vocab words to figure out here. When we learned slope-intercept form, that's the one we're usually using when we do graphing. It's y equals the slope times x plus b, which is the y-intercept. But also you'll come across some standard form here, which is the change in x, so whatever is being multiplied times x, plus the change in y, so something multiplied times y, equals c, a number, usually. For this part, we need to check whether each ordered pair is a solution of this standard form equation. 3x minus y equals 7. See how that looks very similar to this? So 3x minus 1y equals 7. So if we plug in this ordered pair, which is x and y, we would get our answer. So for here we would have 3 times 3 for x minus 1 times 4, just 4, equals 7. So if we did 3 times 3, that would be 9 minus 4 equals 7. And then 9 minus 4 is 5. Does 5 equal 7? No, it does not. So we're going to cross that out and say not a solution. Let's check to see if this one is then. We'd have 3 times 1, because that's what x is, minus negative 4 equals 7. So I plugged in that negative 4 for y. So 3 times 1 is 3, minus a negative 4 equals 7. When you do minus a negative, you could add that, right? So 3 plus 4 equals 7, and then 7 equals 7. So you would say, yes, this is a solution because that equals each other. Moving on to graphing now. So let's graph this equation. We have negative 2x plus y equals negative 3. So let's rewrite it up here. To solve this, usually I like to have it into slope-intercept form. And the way to do that is to subtract this x and move it to the other side. So I have this negative 2x, so I could do plus 2x to get that to cancel out, and then add 2x over here. That would give me y equals, I could do 2x minus 3 or negative 3 plus 2x. So let's do 2x minus 3. And here's my slope-intercept form. So now we can actually plot that out. When x is 0, we would do 2 times 0, which would be 0, minus 3, which is negative 3. When x is 1, we would do 2 times 1, which would be 2, minus 3 is negative 1. When x is positive 2, it would be 4 minus 1, which would be positive 1. Then when x is 3, you would have 6 minus 3 would be positive 3. Let's do a couple negatives. 2 times negative 1 is negative 2, minus 3 is negative 5, so negative 1 and negative 5. Then negative 2 times negative 2 is negative 4, minus 3 is negative 7. So you can see this follows a nice even line here. It also tells us to graph when y equals 2. That means that y is always 2. So these are the values for y, right? So here's the y at the value of 2. If y is always 2, I just draw a line like that across. Now it tells us to graph when x is always negative 1. Well, here's the values for x along this number line, right? Here's a negative 1 spot, so x would always be negative 1 no matter what y is. Now let's graph a linear equation. The distance d in miles that a runner travels is given by the function d equals 6t, where t is the time in hours spent running. The runner plans to go for a 1.5 hour run. Graph the function and identify its domain and range. So we need to input different amounts of time here. And it looks like we're going to start at 0 because you can't run for a negative amount of time. So let's try plugging in 0 for this equation. D equals 6 times 0 hours. And let's write some numbers down in here. And we're going to count by halves, I think, here to give us plenty of room. And then we'll probably count by fives over here. But we're going to pause it just to give us some time to write. Alright, so the graph's all made. Now what we need to do is put in our inputs. We have an input of 0. We'd have an input of 0.5, a 1, and a 1.5. We could have done more inputs, but I'm just going to go with these 4. Let's use this equation then. We have d equals 6 times t. So t is over here on this bottom here for time. Well, when the time is 0, it would be 6 times 0. And we know that anything times 0 would just be 0. So when t is 0, our distance is 0. Our time is 0, our distance is 0. And that makes sense. You haven't started running yet. Now we have 0.5. So if distance equals 6 times 0.5, that would be 3. So we go to 0.5, and then 3 would be right about here. When distance is 1, we would do 6 times 1, which would be 6. So we can plot that. And then when distance is 1.5, we would say 6 times 1.5, which would be 9. So we go to 1.5, plot out 9, and there we would have it. And this would be a continuous function then. Now we need to figure out our domain. So the domain is the time spent, right? So we're going to put t for time. And we know that we can't spend anything less than 0. So 0 would have to be the smallest our domain could be. So 0 would be less than or equal to t, which we know that t would also be, the greatest that t could be is the length that we ran. It says we only run a 1.5 hour run. So that means we can't go over 1.5 in our inputs because that person didn't run any farther than that. So it would be less than or equal to 1.5. So that would be our domain. Greater than 0, less than or equal to 1.5, or greater than or equal to 0. Our range then is how far we ran, our distance. We can't run negative, so the same thing with this. Our range would be greater than or equal to 0. But how far could we run? Well, if we can only run at a 6 mile per hour pace, the highest we could run would be 6 times 1.5, which we found to be 9. So our domain would be less than or equal to, and that would be 9.